2025 is the year. China is finally going to change the landscape of energy production by introducing the world's first commercial molten salt reactor. It's a step into a future where we'll get safer and cleaner nuclear energy. Doesn't that sound exciting? Join us as we uncover how this cutting-edge tech could shake up the energy industry, reduce nuclear risks, and potentially dominate global energy markets by 2030. You won't want to miss this. What is a molten salt reactor? First, we need to know what a molten salt reactor is before dissecting what China is doing. Molten salt reactors, or MSRs, use molten fluoride salts as their primary cooling agent, operating at low pressure. The reactor's design isn't special when traditional solid fuel is used. On the other hand, what is interesting to know about MSRs is that they can dissolve active fuel with the mixture of a reactor. So how does that help, you might ask? It's a major upgrade from all the reactors in operation today. Although this concept may seem pretty groundbreaking, it really isn't from what's to come next. MSRs operate using neutron spectrums, which tell us how the nuclear core is functioning. There are a number of different types of fuel. Much of the revived interest in MSR technology centers around the use of thorium, which can breed fissile uranium-233. Isn't it a cool name? To kickstart this process, an external source of fissile material, such as plutonium-239, is necessary. Lithium beryllium fluoride and lithium fluoride as coolants remain liquid without adding external pressure, even at high temperatures ranging from 500 degrees Celsius to 1400 degrees Celsius. This is in contrast to conventional pressurized water reactors, which operate at around 315 degrees Celsius under significant pressure of 150 atmospheres. The core design of an MSR dissolves fuel in the coolant as fuel salt, with the long-term goal of reusing fuel materials in a useful way, something known as fuel reprocessing. Thorium, uranium, and plutonium can all form suitable fluoride salts, which easily dissolve in the lithium beryllium fluoride mixture. In fluoride forms, thorium and uranium can be separated from each other. As for now, batch reprocessing is expected to be the short-term solution, with the fuel life estimated at 4 to 7 years and achieving high burn-up rates. Intermediate-level MSR designs, such as the advanced high-temperature reactor, incorporate solid graphite particles in the fuel, but these designs aren't that suitable for thorium. The graphite used in MSRs is chemically compatible with fluoride salts, contributing to the reactor design's overall efficiency and safety. Fluoride salts are used because they have very low vapor pressure, even at red heat. They carry more heat than the same volume of water, have good heat and transfer properties, and are not damaged by radiation. Plus, they don't react too violently with either air or water, and thankfully do not react with surrounding structures of metal. But there's a downside to this as well. Having fuel in the solution means that the primary coolant salt becomes radioactive and ends up complicating maintenance procedures. There also needs to be a very close eye on salt chemistry. It needs to be constantly monitored in order to reduce corrosion and prevent a chemical reaction out of nowhere. We definitely don't need that, do we? Beryllium's presence in the salt is also toxic, which leads to its avoidance. This requires higher temperatures to keep lithium fluoride liquid, but lithium fluoride carries a higher uranium concentration than Fly-B, a combination of lithium fluoride and beryllium fluoride, allowing less enrichment. This can be difficult with plutonium. Lithium must be pure lithium-7 in salts. Li-6 produces tritium when neutrons readily break it down. This means lithium must be enriched beyond its natural 92.5% lithium-7 percentage to minimize tritium production. Li-7 is produced in Russia and China today as a byproduct of enriching lithium-6 to produce tritium for thermonuclear weapons. The importance of MSR. China Academy of Sciences, along with researchers from the United States, are working together on solid fuel MSR tech. There is a major reason for doing so. It is the first realistic step towards a fully functioning MSR. Furthermore, the technicality of using molten salts is much lower when they do not have the high activity levels associated with bearing the dissolved fuels and wastes. The experience obtained with component design, operation, and maintenance with clean salts makes it much easier to consider the use of liquid fuels. Using this, the reactor also manages to operate at low pressure while delivering higher temperatures. It's important to maintain efficiency as well. Research and development are currently underway, but it will take a lot of testing before any prototypes are put out. Ever since the project was set up by China, the R&D orientation has improved due to higher interest. Right now, there are two concepts that everyone needs to know about MSR. First, we have the MSR, which will use a thorium fuel cycle, recycling actinides, and a closed thorium and uranium fuel cycle with no uranium enrichment. This will enhance safety and minimize waste, and the entire design is based on a liquid fuel design. The second concept deals with an advanced high-temperature reactor, or AHTR, also known as the fluoride salt-cooled high-temperature reactor. There is also a 5-megawatt prototype under development in China at the Shanghai Institute of Nuclear Applied Physics, also called SINAP, China's Dual Program. China is on the cusp of a breakthrough in clean energy, with its ambitious plans for the Thorium Molten Salt Reactor, or TMSR-SF. This could transform energy production, particularly in the arid northwest regions of the country. Traditional cooling methods are not feasible in many areas, with a low population density and limited water resources. Still, China aims to introduce water-free cooling by 2025 in such areas, using the state-of-the-art reactors it is building. This effort isn't just about providing power, but revolutionizing the energy landscape. In 2011, the China Academy of Sciences launched a massive research and development program on liquid fluoride thorium reactors, called thorium-breeding molten salt reactors. China's main goal is to lead the world in thorium technology by securing complete rights to this energy source. The project is led by the TMSR Center at SINAP, which has a long history of nuclear research, dating back to its efforts in the 1970s to build a 25 MWE molten salt reactor. That project was, however, put to a halt in favor of the Qinshan pressurized water reactor. SINAP's current TMSR development is split into two parts. One focuses on solid fuel, using TRISO fuel in pebble bed or prism block designs. This stream uses a once-through fuel cycle, where the fuel is not reprocessed. The second, more futuristic path involves liquid fuel dissolved in fluoride salt coolant, allowing for reprocessing and recycling. This second option holds great promise and is much more efficient for reducing nuclear waste and maximizing fuel efficiency. A third path involves developing fast reactors designed to consume actinides from light water reactors and tackling the waste products of current nuclear technologies. China's vision extends beyond electricity generation. The ultimate goal over the next 20 to 30 years is to fully develop the thorium fuel cycle while exploring non-electric applications, such as industrial heat production. The TMSRSF stream, though an advanced nuclear technology, only partially utilizes thorium. This system relies on a combination of thorium and fissile uranium, similar to how uranium-238 reactors breed additional fuel. The reactor is designed for high-temperature hybrid nuclear energy applications. First, SINAP planned to create a 2-megawatt pilot station. TRISO particles will be used in this iteration, where both thorium and low-enriched uranium will be introduced separately. On the other hand, the TMSR-LF stream aims for a more ambitious goal, ensuring the feasibility of making this reactor fuel efficient. This system is intended to produce uranium-233 out of thorium, but also makes it quite sustainable. SINAP's plan outlines completing an initial 2-megawatt plant with a 10-megawatt experimental reactor by 2025. The final goal of this project is to build a 100-megawatt demonstration unit that will embody full electrometallurgical reprocessing by the year 2035. In the long run, SINAP looks forward to establishing a 1-gigawatt demonstration plant. Nevertheless, the TMSR-LF project is approximately 1 decade behind the TMSR-SF stream in its development. Also, SINAP has proposed the construction of a TMSF-RLF fast reactor designed to burn minor actinide, a major hurdle in conventional nuclear reactors. Undeniably, the molten salt fuel has a significant advantage over the TRISO fuel by having an essentially infinite burnup and therefore less waste. Molten salt reactors generally reach about 600 degrees Celsius, whereas the TRISO-based reactors are over 1200 degrees Celsius. In the near future, SYNAP is set to concentrate on developing nuclear-standard thorium fluoride and thorium dioxide for use in molten salt reactors. The disappointing lack of progress in constructing the 2-megawatt test reactor is partly due to the difficulty of obtaining a sufficiently pure lithium-7 material supply. The TMSRSF program is proceeding with the pre-conceptual design of the technical plant in cooperation with the Nuclear Power Institute of China and the Shanghai Nuclear Engineering Research and Design Institute. An interesting thing to note about these institutes is that they are refining nickel-based alloys and fine-grained graphite for the structure of the reactors. Two approaches to tritium are being considered alongside methods of tritium storage. The TMSRSF0 simulator is on a 1/3 scale, and its electric heat source is 370 kilowatts. For this, the primary coolant chosen is FLINAK, or, for its full iteration, lithium sodium potassium fluoride with a temperature of 650 degrees Celsius, while the secondary coolant is FLINAK. Another major project is the 10-megawatt thermal TMSRSF1, containing 17% TRISO fuel. This fuel is the same one used in high-temperature gas-cooled reactors. The reactor operates at low pressure with a primary coolant of lithium beryllium fluoride that is 99.99% lithium-7 and a secondary coolant of FLINAK. The core of this reactor is 3 meters tall with a diameter of 2.85 meters, all housed in a pressure vessel that stands 7.8 meters high and 3 meters in diameter. Residual heat removal in this system is achieved passively through cavity cooling. While the TMSRSF1 project predicted an operational life of 20 years, it has been discontinued since. Meanwhile, construction is underway on the 2-megawatt thermal TMSR-LF1 reactor at Wuwei in Gansu, part of a $3.3 billion program. This reactor will use fuel enriched to less than 20% uranium-235 and include a thorium inventory of around 50 kilograms. The fuel for this reactor will be in the form of uranium tetrafluoride. The TMSR-LF1 was also permitted to operate in June of last year, yet another sign that things are moving in the right direction for this project. During its first few years, the reactor will operate on a batch basis, with some online refueling and removal of gaseous fission products. After 5 to 8 years, all the fuel salt will be discharged for reprocessing, where fission products and minor actinides will be separated for storage. The reactor is made to achieve a repetitive recycling process of uranium, salt, and thorium with online separation of actinides and fission products. Over time, the reactor will move from about 20% thorium fission to around 80%. Looking further ahead, SYNAP plans to build a 373-megawatt liquid fuel MSR small modular reactor. This reactor will use a supercritical CO2 cycle, and the project is expected to be completed by the year 2030. This design will allow for various applications beyond electricity generation. The reactor will be loaded with 15.7 tons of thorium and 2.1 tons of uranium, enriched to 19.75%. It will also require the addition of 1 kilogram of uranium daily. Refueling side by side during operations will be done for 8 years before needing to shut down for maintenance on the graphite moderator. The U.S. Department of Energy is collaborating with the China Academy of Sciences on this program, which began with an initial budget of $350 million. Full commercial deployment of the TMSR is expected in the 2030s, marking a significant step toward more sustainable nuclear energy. Other kinds of reactors. Hermes by Kairos Power. Based in the USA, Kairos Power has developed a cutting-edge 320 megawatt thermal fluoride salt-cooled high-temperature reactor, the KP-FHR, which is set to be built at the East Tennessee Technology Park in Oak Ridge, Tennessee. Collaborating with Oak Ridge National Laboratory, the reactor will use 19.75% enriched triso fuel in pebble form, allowing the reactor for active refueling and operating at temperatures up to 650 degrees Celsius. There's a secondary circuit that utilizes a solar nitrate salt mixture, which is composed of 60% sodium nitrate and 40% potassium nitrate for a steam generator. One important detail to know about this reactor is that it has a reliable safety profile and that it contains passive shutdown if things ever go out of hand. Kairos Power's ambitious project includes a reduced-scale test version called Hermes, a 50-megawatt reactor selected by the U.S. Department of Energy in 2020 for a $629 million, 7-year development program. The Department of Energy will contribute $303 million through its Advanced Reactor Demonstration Program. Additionally, in May 2021, the Tennessee Valley Authority, or TVA, agreed to provide engineering, operations, and licensing support for the Hermes project. TVA, which holds an early site permit for the Clinch River site, brings crucial expertise to help move this innovative project forward. Moltex SSR. Moltex Energy's stable salt reactor, also known as SSR, is also an innovative UK-based nuclear reactor design that blends elements of conventional reactors with advanced technologies to enhance safety, efficiency, and sustainability. Unlike most reactors, which rely solely on high-pressure systems to transfer heat, the SSR operates at atmospheric pressure, utilizing vertical fuel tubes in the core to move heat to the reactor coolant. This ingenious design allows for the use of standard industrial pumps that make use of salt with low radioactivity. This greatly simplifies the system and reduces operational risks. The reactor operates at a core temperature of 500 to 600 degrees Celsius. And how does this benefit it? This makes it capable of high-efficiency energy production, and decay heat is safely removed via natural air convection, further enhancing its passive safety features. This reactor is as safe as they come. The SSR's fuel tubes, made of a durable nickel-chromium alloy, are 3/4 filled with molten fuel salt. This fuel salt combines sodium chloride, plutonium, uranium, and lanthanide trichlorides. These fuel tubes are then grouped into fuel assemblies similar to those used in conventional reactors, allowing for compatibility with existing nuclear infrastructure. The tubes are vented to allow fission gases to escape into the coolant salt. Compared to other reactors, the SSR avoids using lithium-7 fluoride for cost reasons. The design allows the fuel assemblies to be moved laterally without needing to be removed from the reactor, enabling continuous refueling on the spot. After 5 years, the depleted fuel assemblies are stored on-site pending reprocessing, adding more flexibility to fuel management. Moltex's SSR design is modular, meaning factory-produced units of 150 megawatts can be manufactured and transported to the site, where multiple modules can be combined to scale the reactor up to gigawatt levels. Each module contains the fuel, pumps, primary heat exchanger, control systems, and instrumentation, simplifying construction and operation. The reactor tank is half filled with coolant salt, which transfers heat from the fuel assemblies to the steam generators through the process of convection. This modular approach allows for cost-effective scaling of energy production and makes the SSR adaptable to various energy needs. Moltex has developed 3 distinct versions of the SSR: the SSRW, the SSRU, and SSRTH, where the W stands for waste burner, U stands for uranium-fueled, and SSRTH for thorium-fueled. Each variant is designed to address different nuclear energy needs. The SSRW, the simplest and most cost-effective version, is designed to burn nuclear waste, as its name suggests. It has a compact core that does not require a moderator, making it efficient and relatively straightforward to build. The SSRW primarily uses plutonium-239 chloride as its fissile fuel, mixed with minor actinides and lanthanides recovered from spent light water reactor fuel, or an SSRU reactor. These specific components are grouped into 451 fuel assemblies in a hexagonal pattern. The primary coolant salt is regulated with zirconium fluoride at a maximum temperature of 590 degrees, while Moltex envisages 750 megawatts as the SSR-W300. The company anticipates a small market for this design. However, it has signed an agreement with New Brunswick Power to begin the initial deployment at the Point Lepreau site in Canada. In 2021, the Canadian government invested up to 50.5 million Canadian dollars in the program. Likewise, plans have been arranged for a plant that recycles used Canadian nuclear fuel. There's a reason that even the Canadian government is involved in this project now. Also, in November 2020, Moltex, New Brunswick Power, and ARC Canada formed a small modular reactor vendor cluster to progress the development. They have started a pre-licensing vendor design review of the SRSW. This allows them to get one step closer to licensing the SRSW. The SSRU, described by Moltex as its global workhorse, is significantly larger and costs more, but has a higher market application capacity. This variant runs with a thermal neutron spectrum and incorporates low-enriched UF fuels. Graphite is inserted in the fuel assemblies to slow the reaction. The core is made larger to afford operation at higher temperatures than fast-spectrum SSRW. The SSRU operates at a minimum channel temperature of 600 degrees Celsius, with the coolant salt being a eutectic mixture of zirconium fluoride and sodium fluoride, with a bit of zirconium difluoride. Apart from power generation, the SSRU is intended for hydrogen generation, and thus it has a strong platform in the clean energy market. The reactor can also breed thorium to produce uranium-233, making it even more sustainable than it already is. The company estimates that the first SSRU plant will become commercially available by the 2030s, originally targeting the United Kingdom, where the technology could be deployed to replace retiring coal and combined cycle gas turbine plants and tap into a major opportunity. The SSR-TH version uses thorium in the reactor and its breeding capacity to produce U-233. In this design, thorium is dissolved in the coolant salt, and as U-233 is produced, it is dissolved in a bismuth layer at the bottom of the salt pool. The SSR-T can operate as a fast reactor, potentially adding plutonium and minor actinides for further fuel flexibility. However, there will also need to be contingencies set in place before such a reactor can be materialized. It is because the faster the reactor is, the more chances there are of it becoming unstable. In addition to the reactor designs, Moltex has introduced its grid reserve molten salt heat storage concept, which allows the SSRW to supplement intermittent renewable energy sources. This system enables the SSRW reactor to increase its output to as much as 900 megawatts during peak demand by drawing on stored heat from the secondary coolant salt. This ability to ramp up output makes the SSRW a versatile complement to renewables, helping to stabilize the grid while providing clean, reliable nuclear energy. So, if we recap what we've understood about the three different reactors in the SSR category, it is clear that SSRU is the most efficient out of the three. Though it offers more power, there are also higher maintenance costs that are associated with it compared to SSRW and SSR-TH. Mark 1. Pebble Bed, FHR. With other partners, the University of California, Berkeley, Oak Ridge National Laboratory, and Westinghouse developed a pre-conceptual, fluoride-cooled, high-temperature reactor design in 2014. The Pebble Bed FHR, which can be constructed in modules, has a target operating temperature of 700 degrees Celsius and has an annular core configuration. The reactor operates with smaller fuel pebbles with a diameter of 30 millimeters, compared to gas-cooled, high-temperature reactors. The project also analyzed how FHRs can be combined with a Brayton combined-cycle turbine to improve specific output. Also, a passive decay heat removal system was included in the facility's design because the safety of the reactor requires heat removal, even without power. A unique feature of the reactor is the annular pebble bed core, which has negative void reactivity to enhance safety by decreasing reactivity in the case of a loss of coolant. Such a passive design shows that FHR technology can offer not only base load power generation and peak load generation, but also high safety standards in its integration. The timeline of these reactors is well underway, and it won't be until the next few years when we'll be able to see their progress. However, one thing is clear: we might be on the brink of tapping into an energy source that we haven't explored much before. Thanks for watching, and we'll see you next time.